So first, let's talk about what is the difference between implicit and explicit. We have many relationships between variables that are expressed implicitly. For example, if we have the equation of the circle, which is given by x squared plus y squared equals 1, that's not specifying the value of y directly, but is defining y implicitly. There's not an expression y in terms of x. Okay? Now, this equation does not represent a single function because the graph will fail the vertical test line. So we have this situation here where we have a circle, and of course, if we just give a line, we have that it's going to intersect 2 points. So this is not really giving me a function. However, it gives me 2 functions, which is the function y equals the square root of 1 minus x squared, and also the negative, the function below, minus the square root of 1 minus x squared. Okay? So the blue circle here is this function, the red circle here is this function. Now notice that this is an implicit relationship and this is explicit now. Here we're given y in terms of x explicitly. So now in the common situations, we have identified 2 explicit functions that form the circle, and we can get the derivative using the chain rule. So if we have 1 equals square root of 1 minus x squared, then dy dx is going to be minus x over square root of 1 minus x squared. And similarly in the case of the negative root. So only going to change the sign over here. Now the equation x minus y squared equals 0 implicitly defines also 2 functions. We're going to find y equals the square root of x and y equals minus the square root of x. Okay? So as you can see, finding derivative for these cases might be a little bit complicated because you are getting 2 functions, right? And then you have to get 2 derivatives. So instead of doing that, now what we want to do is find a way of doing the derivative without necessarily have to put one function in terms explicitly of the other, one variable explicitly in terms of the other. And because in some cases we're not going to be able to do it. Over here we can actually find who y is and tell, okay, y is the square root of x and y is minus the square root of x. But if we consider something like x plus y cubed minus xy equals 1, this function has no way to be explicitly defined. I cannot just write y is equal something in terms of x. Okay? And so it's impossible to separate and to find a explicit version of the derivative. So for this is that we need to define a different way of finding the derivative. Notice that in some cases like this, the variable y can give me even 3 or more functions depending on the domain. So noticing here we have the line, we have this purple, which is another one, and the green line. So this is giving me all these different points that are part of this implicit curve, and we're definitely not able to split them into functions. Now to calculate then the derivative implicitly, we're going to use the chain rule. Since we can consider that y is a function of x, so y is a composed function of x. So if we want to calculate the derivative here in x squared plus y squared equals 1, we're going to calculate the y dx directly from the equation. And so what we do, once that we do that, is we're going to find the slope of the unit circle at a certain point. So you all can see that we can do the same things that we usually do. Okay, So now if we consider x squared plus y squared equals 1 and we apply the derivative of x squared is going to be 2x, and that's just as usual. Now the derivative of y squared can be considered as the same thing, right? But notice that when we have x squared plus y squared equals 1, this y of x is a function of x. So there is this is considered a function. So this is like a chain rule situation. So we can do 2y of x, 2 minus 1, times the derivative of the function inside, which is going to be y prime of x, or I can write dy dx depending of whatever your taste. And sorry, here the derivative of 1 is 0. Okay, so overall this is going to be 2x plus 2y times y prime equals 0. And from here we can find out who y prime is. So now y prime, or 2y y prime, is going to be minus 2x. So that means that y prime is going to be minus 2x over 2y, or minus x over y. Okay, and so now this gives a value for the derivative in terms of x in the function y. So going back to this situation, if I use the point 1/2, notice that and this is going to be square root of 3 over 2. This is a typo here. So if I have the point 1 square root of 3 over 2, this is going to produce a slope of minus 1 over square root of 3. Notice that that happens because this is minus 1/2 and square root of 3 over 2. So out, and we're going to get minus 1 over square root of 3, and the situation that this is 1/2. And when we have minus 1/2 down here, we get the positive. Okay, so we're getting these two slopes. Now, so that's the trick for doing the implicit differentiation. Now we can have more complex functions in here. So for example, we want to find out y prime for the function sine of xy equals x squared plus y. Notice that indeed we cannot explicitly define y in terms of x. So we have certain steps that we can take for this. So we calculate the y dx directly from the equation. Let me do that on the board. So we have sine of x times y equals x squared plus y. And notice that everything comes into play. Now we have to do the chain rule. This is a derivative of sine, so now this is going to be cosine of xy, because that's the derivative of sine, but times, and now this is a product rule, so we now have 1 times y plus x times 1 times y prime. Remember that this has a chain rule, so the derivative of y can be 1, but we need to multiply always by y prime. Every time that we take derivative of y, we need to multiply by y prime. On the other side, this is going to be 2x plus 1 times y prime. And so that needs simplification, of course. We get y cosine of xy plus x y prime cosine of xy equals to x plus y prime. So now the thing that we need to do next is put everything that has y prime on one side, and so that is going to yield the following. And now at this point we factor y prime, and that's going to allow us to finally find what y prime is. Notice again that y prime is something that is going to be in terms of y and x. So when we're working with tangent lines, we're going to need both the value of x and y. So if we're going to find a tangent line in here, I better have the values of both x and y. Now let's go for another example just to showcase that. We're going to find the equation of the tangent line to the curve x squared plus xy minus y cubed equals 7 at the point 3, 2. Notice that something important is that you make sure that this point is actually part of this curve. So if you plug 3 in here, you should get y equals 2. Okay? So if you plug 3 equals here, you get 9. 9 plus 3y minus y cubed equals 7. But so if you plug the 2 now, or let me do this in the board so it doesn't get confusing. So first we want to verify we have this curve x squared plus xy minus y cubed equals 7. So I want to verify that this point 3.2 that they're saying goes through this curve works out. So for that I plug in x and in y. And so now this is 9 plus 6 minus 8. And it turns out that this is 15 minus 8 is actually 7. So yeah, it holds both sides of the equation. So we know now that that point belongs to that curve. So next what we need to do is now we can get the tangent line. Let's take we take derivatives. And the derivative of x squared is 2x. The derivative of xy is a product rule. So the derivative of x is 1 times y plus x without derivative times 1 from the derivative of y times y prime, because we just did a derivative in terms of y, minus 3y squared times y prime, because we took derivative in terms of y, equals 0, because that's the derivative of 7. Now we get together terms with x and without x, so 2x plus y is equals to 3y squared y prime minus xy prime. Okay, I'm just sending everything to the respective size. So now y prime 3y squared minus x is equals to 2x plus y. And so that implies that I can find that y prime is 3y squared minus is 2x plus y over 3y squared minus x. Okay, now I need to plug, of course, the slope is y prime in 3, 2. And so that is 2 times 3 plus 2 and 3 times 2 squared minus 3. So one of the things is hopefully we don't have a 0 on the denominator for this situation. So otherwise we just going to have an infinity slope, which is going to give me a vertical asymptote situation. But in this case, this is 8. And in here 3 by 4 is 12, minus 3 is 9, so 8 over 9. So this is my slope. I have the point, so I use the point slope formula, and I found the equation of the tangent line. Okay, notice this equation is going to be transformed in 8 over 9 minus 2/3, and is representing this tangent line that is coming in this point 3, 2. This is the graph of this actual curve. You can find this type of graph using a graphing tool, like the Desmos Graphic Calculator or others, and then we can paint where the point is going to be located. Notice that this by itself is not a function. Notice that the vertical line test fails here badly. Okay, so now derivatives obtained by implicit differentiation typically depend on x and y. And so hence we need that the slope of the curve at that particular point x and y is going to require plug in x, plug in y. Okay, don't forget that you need both coordinates. Now, let's do one example more of this. Now, let's take the tangent line from the function 2x plus y to the 1/3 equals y at the point 4.4. So 2x plus y to the 1/3 equals y, and then the point is supposed to be 4.4. Now notice that if I plug 4 and 4, we get 8, right? And 8 to the 1/3 is 2. So this is 2 times 2, which is 4, which is equivalent to y. So at this point, yes, it holds this relationship. Okay. Now we take derivative to find the slope. And this is a chain rule, of course. So we have 2/3 x plus y to the 1/3 minus 1 times, and then 1 plus 1 times y prime, and equals to 1 times y prime on the other side. Now this is going to be 2/3 x plus y to the minus 2/3 times 1 plus y prime. So that means that I can just split this in 2. Okay, and from there we're gonna find out what y prime is. So y prime is gonna be 2/3 of x plus y to the minus 2/3. And notice that that's going to be divided 1 minus 2/3 x plus y to the minus 2/3. This is doing some algebra. Remember, we put this on the other side, factor y prime, and then later divide. So that's why we get in this part. Now, if we're going to get the slope m is equals to y prime and 4, and so I gotta plug in here x and y, so that's gonna produce an 8. Okay, then we can simplify the cube root of this is 2, so this is 2 to the minus 2 at the end. So this is 2/3, and 2 to the minus 2 is just 1/4. And so this is 2/12 on the top, and on the bottom it's going to be 10/12. And if we simplify this is going to be 2/10. This is going to be 1/5. Okay, and so that's the slope of the tangent line. Now we have the point as well. So with that, we can find the equation of the tangent line. Okay, so we have this slope of the curve 1.5, and we find this tangent line in here with the point 4.4. Okay. Now, we can also take high order derivatives with implicit differentiation. We're not necessarily stuck just at the first derivative. So just to get an example of that running, we're going to take the equation of the circle and find the second derivative. So we start with x squared plus y squared equals 1. And so after taking derivatives, we have this situation. And so y prime is minus x over y. But now we can take the second derivative. The derivative of this is going to be y to prime. And then I gotta multiply by y prime because I just did derivative here. And on the other side, I have a quotient rule. So I have minus 1 times y plus, minus x times 1 times y prime divided by y squared. Okay. And at this point, I can simplify a little bit over here. This is minus y and then plus xy prime divided y squared. But remember that this y prime is minus x over y, so I can just replace that. I can just replace that, and I can just replace y prime here as well. So instead of y prime, I'm going to be writing minus x over y. And so now that implies that y to prime is equals to y over x times minus y plus, or actually minus x squared over y divided by y squared. I can of course cancel out one of the y's. So y to prime is now going to be minus y over x, and then this x is going to cancel one of this, minus x over y, and then I'm going to cancel this y with one of the y's here. So this is going to be like this, or I can rewrite this as minus y xy minus x y squared, or this will mean minus 1 over x minus x over y squared. Okay, so kind of convoluted. It requires a lot of steps, and it requires that we replace what we initially have. So notice, taking the derivative of y prime gives me y to prime times y prime, right? Because we're taking the derivative with respect to y. And on this side, we get y prime again, but we have information of what y prime is in terms of x and y, so we get to replace that. And then we get to simplify. And at the end, we obtain y to prime, a function used in terms of x and y.